Wind has been a source of clean energy for more than 1,000 years. All across the globe, the use of wind energy is becoming more and more prevalent. But only during the last decade, its use on a large scale has been planned and implemented. This development has come as a result of advances and improvements in wind turbine generator designs. Today, wind power is the world's fastest growing segment of the power generation business, with growth rates of sometimes more than 40%. However, this massive growth brings new challenges.
You need transmission lines to move wind energy to market.
Wind power faces some major challenges. The areas ideally suited for wind power generation are usually far away from where energy is needed most. And the intermittency of wind is an important factor that requires attention.
Traditional electric power grids weren't built for long-distance energy transmission. They're actually regional and local systems that grew together, evolving over time. You can't simply feed 3,000 megawatts or more into your local high-voltage grid, even if you're lucky enough to have such a grid nearby. Moving large amounts of power from where it is generated to where it's needed is a problem for large-scale modern wind power projects, and HVDC systems are the solution that help get that power to market.
High-voltage direct current transmission systems, HVDC systems, hold the answer to this challenge. The wind turbine's AC power output generally has a voltage of 11 to 13 kilovolts. This is then stepped up to typically 33 kilovolts, and finally to transmission voltage levels 138 kilovolts or above, and is then connected to an HVDC converter station. Here, it is transformed to high-voltage direct current for long-distance transmission, and finally converted back to AC to be fed into the local power network at the destination area. HVDC systems are an important contribution to the development of smart and reliable transmission systems. They make it possible to transmit huge amounts of electric power over long distances in the most efficient manner. HVDC systems offer a number of other benefits. The security of our power supply is highly important in our daily lives. HVDC systems can significantly improve the supply security with its incorporated firewall function, similar to computer network firewalls. This feature has been impressively demonstrated through the prevention of a number of blackouts. Additionally, transmission losses are typically 30 to 50% lower than with AC systems at the same voltage and power, depending on the voltage level and individual construction details. At a transmission capacity of 3,500 megawatts, AC transmission lines can have losses of up to 15% over a distance of 600 miles. Compared to this, DC lines losses amount to only 4.54%. Typically, large-scale AC needs 2 parallel redundant systems with 3 conductors each. DC needs only 1 bipolar system with 2 conductors. This means DC systems require considerably less space than conventional AC transmission systems. They allow for a significant reduction of the overall environmental impact associated with overhead line construction and help to substantially reduce right-of-way costs. AC transmission requires a comparatively low investment at first sight. However, further investments for reactive power compensation and control are required for HVAC transmission over longer distances. HVDC systems involve a higher initial investment for the DC terminals, but do not require additional devices for long-distance transmission. So, long DC lines actually become less expensive than AC lines. Depending on the voltage level, savings of 30 to 70% can be achieved when compared to AC lines. As a result, HVDC technology is especially favorable for long-distance transmission applications. Of course, HVDC is ideally suited to connect new, remote sources of electricity to the grid and provide access to the power grid where there was none before. The next era of HVDC technology, Siemens ultra-high voltage DC, is characterized by its innovative 800 kilovolts voltage level, which now facilitates the transmission of up to 8,000 megawatts and further reduces losses.
The basic principle of operation of an HVDC system is the conversion of AC to DC and vice versa through converter valves. Advanced power electronics are the key. The converter stations link the HVDC transmission line to the AC systems at the power generation facility and in the load center. This way it becomes possible to bridge distances of 1,200 miles and more and get the power to exactly where it is needed.
Renewable energy sources can fluctuate, and as a result, the output of the generators and the amount of power transmitted do the same. Conventional energy sources, such as combined cycle power plants, can help compensate for such fluctuations in some applications, making wind power integration into the network easier to manage. A fast startup gas turbine, for instance, could ideally complement a wind farm and produce electricity during lulls. And smart grid technology from Siemens enables the grid to proactively balance the various energy sources. As the only energy infrastructure supplier serving the entire energy conversion chain, Siemens is uniquely positioned to supply these solutions.
Everybody understands that transmission is the big challenge facing renewable energy.
HVDC is gaining in recognition worldwide as it helps transmit much more power from remote places to where it is needed most. By using HVDC, more electricity can come from clean sources.